Hello everyone, this is Chris back again with the Ancient Scholar. This is video 3 in a several-part series on introductory pathophysiology. I'm going to continue talking about the cell environment. On the last video we had discussed some of the basic anatomy and physiology at the cellular level, primarily talked about the major organelles and some of their major functions, for the most part in a homeostatic environment. So what I want to talk about today is I just want to focus a little bit in on the cell membrane and kind of what its function is. So the cell membrane, or the cytoplasmic membrane, is a membrane that surrounds the cell, and it's what we call selectively permeable. That means some substances can pass through it quite easily, while other substances are unable to pass through this membrane very easily. And the way that this works is the membrane is composed of what's known as a phospholipid bilayer. That means on the very outer layer there are basically phosphorus-based molecules. And then in the middle we have lipids, and then on the very inside surface of the cell we have another layer of phosphorus-based molecules. Well, what does this mean? Well, when we talk about substances entering the cell, this is going to go back to chemistry. There are basically two types of substances. There are substances that have a charge to them. That means that they are not electrically neutral. They either have an excess of electrons, if you will, or a deficit of electrons. And if they have more electrons, they are negatively charged. And if they have less electrons, they're positively charged. As we know, most of the nonmetals will have more electrons because they have a property known as electronegativity. They really like electrons. And this would include things like, or could include things like oxygen, nitrogen, fluorine based molecules, where you have a really electronegative element, non-metal typically, and you're talking about an ionic kind of bonding situation. However, when we talk about our metals are not electronegative. They don't particularly like to hold on to their electrons. They like to get rid of their electrons. In this case, they'll give their electrons up to other molecules or other substances or other atoms, and these would include things like sodium. Never mind the clock, that's a loon howling, kind of a novelty gag gift. In any event, things like sodium, calcium, potassium, and magnesium are all metals. They all give up their electrons, and we generally see these as positively charged substances. And then we have neutral substances, substances that don't have much of a charge. So let's just talk about these for a minute, if we will. Your charged substances, either your anions, which have a negative charge, like chloride, or your positively charged substances that have given up electrons, like sodium and potassium, generally are not very good at getting through the cell membrane. And the reason being is, in the middle of the cell membrane there are lipids. Lipids are non-charged for the most part. They don't have much of a charge. They don't really like water all that much. They don't do much with water. They don't dissolve in water. Charged particles dissolve in water and move in water, but non-charged substances really don't. So these charged particles, like sodium, chloride, potassium, and magnesium, cannot easily get through the center of the cell membrane. Now the outer part of the cell membrane and the very inner part, the phosphorus-based part, charged particles can interact with, but they can't get through the middle of the membrane. However, water is free to go through the membrane in and out of the cell all day long. So this is where the concept of a selectively permeable membrane comes into play, that only charged particles or charged substances typically can't get through, and we typically call these polar molecules. because in a lot of cases they can have a pole to them. One side's positive, one side's negative. The only exception being water. And we do know that water is a polar molecule because the oxygen in a water molecule is electronegative. It likes the electrons, and it kind of hogs the electrons away from the hydrogen, so the oxygen part of water becomes a little negatively charged, partially negatively charged, and then the hydrogens kind of take on this partial positive, and that's actually how things like sodium and chloride can dissolve in water because of that interaction. But water can get through the cell membrane. All these other charged and partially charged substances, for the most part, can't. So the way that they can get through the cell is through a channel of some sort, or maybe they can interact with some sort of receptor. Generally, these receptors or channels are protein molecules that go through the cell membrane itself. So I went ahead and drew a little picture here. So if you can imagine, this is the outside of the cell here. This is the inside of the cell here. These little balls are the phosphorus-based molecules, and then these little tails here are the lipid-based molecules. So I have a phospholipid layer. So I have phosphorus on the inside, phosphorus on the outside, and in the very middle I have lipids. So water can easily pass through here, but charged particles can't get through the lipid-based layer in the middle. However, I have a protein channel here, and those particles are able to get in and out through this protein channel. An example of one such example is the sodium-potassium ATPase pump, and it is one of the principal pumps in the cell, and it can help regulate the movement of potassium and sodium. In a normal cell, there will generally be more potassium inside of the cell than outside, and more sodium on the outside of the cell than the inside. There's a difference. More potassium here and more sodium here. And then we know that if sodium rushes into the cell, potassium rushes out. That's called a depolarization, and that's how things like neurons and cardiac cells work, by depolarizing the charge potential across the membrane. When the cell is damaged, or maybe it's in a shocky state where it's not getting nutrients and can't make ATP, sometimes these channels and pumps begin to fail. So in the case of this sodium-potassium pump, if it were to fail, and we can talk about the reasons it can fail later on, if it were to fail, sodium could actually rush into the cell, and if there's lots of sodium inside of the cell now, well, because this pump is no longer working and sodium just rushes right on through, and the pump can't pump the sodium back out because it doesn't have energy or it's damaged somehow. Well, what's gonna rush through the membrane in response to all that sodium being in the cell now? Well, water. So water's going to rush into the cell. The cell's going to take on water, and it could potentially lyse or rupture and die. And that's actually one of the pathophysiological mechanisms at play when we talk about cell death in somebody who's critically ill or injured, is the fact that the cell can't make enough energy. It's the membrane channels, pumps, and receptors begin to malfunction for a various number of reasons, and we have sodium and potassium going places where sodium and potassium doesn't normally go, and we have water going places where water doesn't normally go, and of course that can cause cell lysis. Okay guys, so that's just kind of a bit, and again, most of this information you've already covered in your prior classes, but just getting everybody on the same page so when we start talking about things breaking down and not working, we will have some foundational material that we've already covered. Okay guys, take care.